All right, sounds good. Thanks everybody for coming. Today we're gonna have Ali talk to us about Garuda and Pari, faster and smaller SNARKs via Equifficient polynomial commitment. Thank you for coming, Ali, and go ahead and take it away.
Sure. Thanks, Matan. Yeah. Hello, everyone. I'm Ali, and I'm a first-year PhD student at Penn. Actually, in 10 days, I'm going to be second-year student. This is a joint work with Pratyush and Michael. We present two SNARKs, Garuda and Pari, and that Equifficient word is just a made-up word. So we will see what that means. Okay, today we're going to talk about the SNARKs a lot. So let's first see what SNARKs are. Succinct, non-interactive arguments of knowledge, or for short, the SNARKs are protocols between a prover and a verifier, such that the prover wants to convince a verifier that he knows a witness, such that a computation F over some public input X and this witness is satisfied. And the first step of almost all of these SNARKs are the phase of setup, which means that the computation is expressed usually as a circuit, and the setup algorithm uses that circuit to output the prover key and the verification key, and we give those keys to the prover and the verifier, and the prover having access to the proving key and the public instance and the witness that he knows, outputs a string pi, which we call proof for that computation. And the verifier having access to the verification key and the public instance and the proof generated by the prover wants to decide whether f of x and w actually is 1 or not. So he has to either accept or reject. So in order to call it actually a SNARK, there must be some properties. First of all, this system should be complete, meaning that if P is honest and actually knows a valid witness, then V has to accept the proof pi. And it should be knowledge sound, meaning that if P does not know a valid witness, then V has to reject. So it's actually in soundness. So for knowledge soundness, it means that if the verifier actually accepts, it must be the case that the prover actually knows a valid witness, such that it satisfies the computation F. And it should be succinct, meaning that the size of proof and, of course, the verification time should be non-trivially smaller than the computation F. So it should be sublinear to the size of the witness and the computation. By the way, at any point, if you have any questions, just to stop. Okay, after defining the SNARKs, the first natural question that arises is that, well, SNARKs kind of magically compress computations. So how small this proof size can get? Like, aside from the theoretical aspects, so in blockchains, we have to pay gas for each proof that we post on chain. So the smaller, the better. So Groth in 2016 came up with the lower bound, and it's just specific for fully algebraic SNARKs. It says that every algebraic SNARK that uses pairing-based cryptography should have at least 2 group elements in its proof size. That's a known lower bound. So it means that in 120 bits of 28 bits of security, it should be 144 bytes. And he himself introduced Groth16, which had 3 group elements, which was 192 bytes. And a concurrent work in 2024, which is called Polymath, showed that by using random oracle, we can reduce the proof size of Groth16 to 176 bytes. So if you think about it, this Polymath actually doesn't have to do anything with the lower bound, because this lower bound is talking about fully algebraic SNARKs. So we shouldn't use random oracle. So using random oracle is just for bypassing this lower bound. So in this paper, we ask that can we go lower than 176 bytes? So that's the first question. The second question that we've kind of been dealing with for the last decade in SNARK literature is that how fast can we prove? So proving has a large overhead, that's a fact, and it can be as large as 1,000 times over the native computation. So how can we reduce it? And there are kind of two mindsets to deal with this problem. One mindset is that we can use free addition gates, like most of our computations is comprised of many addition gates, many linear gates. So if we can have them for free, we can kind of have efficient provers. That was a mindset which was supported by circuit-specific SNARKs back at 2016, where we had like Pinocchio, Groth16, GGPR13. They had this native support for free addition gates, which I won't go into details. And the second approach that industry is heavily using that is using custom gates. So there are some specific computations that we use in a circuit repeatedly, and they might be expensive. For example, elliptic curve operations or S boxes, which are usually high degree, or for example, we want to do range proofs for all of the wires in a circuit. So for these repetitive and expensive computations, we can have custom gates, and it was introduced in HyperPlonk. So this is another approach to deal with the proof cost. Unfortunately, we don't know any existing SNARK that supports both of these approaches. Like we don't have any SNARK that has free addition gates and also supports custom gates. So the second question that we ask in this paper is that can we fix this?
So by the way, how free is free? Is it really that like a computation which is like a million quadrillion addition gates is just the same prover? I mean, it can be the same prover cost because the prover needs to compute these additions.
It doesn't have cryptographic cost.
Okay.
It doesn't come up as in MSMs or in group operations.
So in the overhead that you do over just native computation, it just doesn't show up.
And that 1,000 that I had, for example,
yeah,
it was the overall overhead. Like,
okay.
yeah, it might be counted. That's just a rough figure of what are the what numbers are we talking about?
Okay, no worries. Yeah, you can keep
yeah.
going.
What is MSM?
I'm sorry.
What is MSM?
A multi-scalar multiplication. Like you wanna add a bunch of group elements.
So you have a bunch of group elements in G1 through Gn, and you want to raise them to like alpha 1 through alpha n, and then you want to multiply all this together.
Yeah, it's just a common operation in designing SNARK. Okay, so what are our contributions in this paper? We answer to both of these questions positively. First, we introduce Pari, which is the smallest known SNARK with the proof size of only 2 group elements plus 2 field elements, which means that if you take a look at these numbers, Pari would fall over there with 160 bytes. It's smaller than Polymath, but it's still, even though we use random oracle, we're still greater than the lower bound of processing. So it's still
no, but the lower bound is not applicable for you, right? Like, because you don't, you are in a different model.
Yeah, we're in a different model. That's just for something to keep in mind. Yeah, some just that's the only lower bound we know.
No, like
SNARKs.
you could
Yeah,
go even lower than that. There's no reason to believe that you can't go lower than that using random.
you're absolutely right. But we don't know. We don't have any lower bound on universal SNARKs. Yeah, that's a open question. Like, first of all, how can we touch that lower bound, and how we can bypass that with random oracle or on different models?
Could you just remove the 2 boxes?
I'm sorry.
Could you just remove the boxes on top?
Oh,
Just click.
I'm also running some benchmarks, so my laptop's pretty slow. Okay. So our second contribution, yeah, I'm sorry about that. I don't know.
Top audience.
Everything good?
Yeah.
Okay, so the second SNARK that we present is Garuda. Garuda is the first SNARK with free linear gate, like free addition gates, that also supports custom gates. So just for comparison, So Groth16 only supports free addition gates, and it doesn't support any custom gates. If you want to use custom gates, you have to unroll your computation. And the HyperPlonk supports custom gates, but does not have free linear gates. So by combining the best of these two worlds, we can beat both of them. And in this chart, you can see that we implemented and evaluated on the invocations of rescue hash functions, and that's the result we get. Okay, these are the two
What's
contributions.
like the proof size for?
This is log. Concretely, I don't remember, but yeah, it's log. Yeah. So both of these constructions are in random oracle model and AGM, algebraic group model. Unfortunately, both of them are circuit specific. So one open question that I will discuss at the end, that how can we make this universal or transparent?
So maybe a different question, like why are these in the same paper? Like why?
Because they use the same technique. Yeah. So that technique is EPC schemes. So we introduced this new tool that we call Equifficient, which is a made-up word again. Polynomial commitments. It means that equal coefficient polynomial commitments is a new scheme that I will describe. And so we instantiate this scheme into two regimes. First, we instantiate it in univariate regime. We use that to build Pari. And then we instantiate it in the multivariate regime, and we use that to get Garuda. So that's there's a shared tool that is using both of them. I guess there's a message in Zoom. If anyone has access and can read that to me, maybe.
Yeah, you can go ahead. I'll tell you after this slide.
So our methodology, like the way we construct these SNARKs, is exactly the same as the existing SNARK methodologies, which is you give me a PIOP and a PC scheme, and I have a compiler that will compile this to a SNARK. So it's a known methodology. We're still using this methodology, but the thing is that some of the checks, that the PIOPs in previous works do, we kind of do those checks on the EPC scheme. Like our EPC scheme is not just merely a compiler to materialize the polynomials outputted by the PIOP. It does more. So there's still this methodology, but these two components are a bit different.
So Kwong asked if there's any univariate. Sorry, let me read off the question exactly. Are there any universal SNARKs with free addition gates? And then he asked maybe Marlon.
With free addition gates, no,
Yeah.
Marlon, you have to pay with non-zero elements of the matrices.
So do you know of any universal SNARKs that have free addition gates? Maybe just a property of like circuit specific setup SNARKs that have free
Universal
addition because you compile that into the circuit specific setup.
There's this paper by Groth and Mary Muller, and it was before the Sonic paper. It has quadratic universal SRS, and I believe that supports free addition gates. But that's the only interestingly, that's the only fully algebraic universal SNARK that we know of. All the other universal SNARKs are by random oracle. So yeah, I'm guessing that's the answer.
Okay.
Yeah.
Thanks.
Okay. So a little bit of background. What are polynomial PIOPs? What are PC schemes? So I just go through them. What is a PIOP or polynomial IOP? Interactive oracle proof. It's a protocol between a prover and a verifier where the prover outputs polynomial oracles to the verifier, and the verifier randomly challenges, like sends out random strings to the prover, and at the end of this interaction, the verifier outputs a query set. He wants to locally open those polynomials, query those polynomials on certain query set, and after getting those evaluation, the verifier has to accept or reject. So it still has the standard notion of completeness and soundness, meaning that if the prover is honest, the verifier has to accept. And interestingly, we don't go into knowledge soundness for the PIOP, and we will see that our PIOPs does not need to be knowledge sound. So we'll get to that. But for soundness, it means that if the prover is not honest, so then the verifier has to reject. Any question on the background? Okay, and our second ingredient is the PCA scheme. So polynomial commitment scheme is a scheme that you kind of put a polynomial in a box and you send this to some receiver, and you have this guarantee that you cannot touch this polynomial, you cannot change that, and the receiver can later on locally open this polynomial, locally evaluate this polynomial on some points. So this usually starts with a setup algorithm. The setup algorithm takes a maximum degree n, which then our algorithms are going to operate on, and it outputs a committer key and a verification key, and the sender has this commit algorithm, commits to the polynomial with the committer key, and gets a very succinct commitment, and sends this commitment to the receiver. The receiver later on wants to evaluate that polynomial on a point z. The sender does the evaluation and provides a proof for that evaluation and sends the evaluation with the proof to the receiver, and the receiver at the end has to decide whether this evaluation was correct or not by only having the proof and the commitment and the evaluation result. So it has to be complete, meaning that if this polynomial actually evaluates to v on the point z, the receiver has to accept, and it has to be extractable, meaning that if the receiver check passes, it must be the case that the sender actually knows a polynomial p such that it satisfies this evaluation. P of z is equal to v. Any question? Okay, so we know from the literature that we can combine PIOPs with PCs to get a SNARKs. And it's usually done in this way, that the setup algorithm of the SNARK would just get the maximum degree of the PIOP specification and use the PC setup to get the committing key and the verification key, and the overall prover key and the verification key of the SNARK will be just the verification key and the commitment key of the PC. Okay, and then the prover and the verifier start interacting. All of the oracles that are outputted by the PIOP prover are then materialized by the PCA scheme and sent to the verification. And verification again just invokes the internal PIOP, outputs some random challenges, and at the end, again, we have a query set. We query those polynomials, but instead of querying those polynomials, we ask for the evaluations of those committed polynomials. And the prover just provides opening proofs for those evaluations and sends the evaluations with the opening proofs to the verification. And at the end, it had to decide based on two predicates, which is like one PIOP verifier has to accept and PC scheme has to pass. The PC check has to pass. Okay, and we can transform this to non-interactive arguments with Fiat-Checker. So that's a known paradigm that we know. Okay. It was a quick background. So now let's talk about how this, like previous methodologies, are adapted to create SNARKs for R1CS. So what is R1CS? R1CS is an NP-complete language which consists of triples of A, B, and C. And we say that this instance is satisfied if there exists some W such that if we concatenate X and W, this Hadamard product holds, meaning that AZ Hadamard product BZ is equal to CZ. That's the R1CS problem. And we usually tend to convert our computations to R1CS instances. Okay, so this is an important part. So usually the PIOP-based SNARKs out there decompose their provers to prove two checks. So the prover proves two things to the verifier. First, it sends out three, like for example, three polynomials to the verifier, which are ZA, ZB, and ZC. and tries to prove two things. First of all, the linear check. The prover wants to prove that ZA is actually AZ, ZB is actually BZ, ZC is actually CZ. And A, B, and C is somehow known to the verifier, like a computation commitment or something. And he usually, after that, he convinces the verifier that this Hadamard product holds, meaning that ZA times like Hadamard product ZB is equal to CC. So these two checks are usually done. If you take a look at the literature, Spartan, Marlin, or even Plonkish SNARKs. So Plonkish SNARKs, this linear check is kind of equivalent to the permutation check. Like this is equivalence there. But the nonlinear check is still there. Okay, so this row check turns out to be very easy. Like you just send four commitments to these polynomials, like ZA, ZB, ZC, and some polynomial Q. We don't care what these polynomials are. We will talk about them later. But just note that just by sending a constant number of polynomials and just querying them in one point, the verifier can be convinced that this Hadamard product holds. So that's pretty easy. But unfortunately, the linear check is the most expensive part. So in Marlin, there's a big link check, which I don't understand myself. So, and also in Plonk, we do this permutation check. So it requires numerous commitments, opening evaluation proofs and stuff. So note that even if we have the best polynomial commitment scheme out there, like the fastest hash-based post-quantum PCS out there, still we have this bottleneck. We have to materialize these polynomials and provide commitments and openings for these polynomials.
So, okay, you gave us some sense of how much information you need to send to do the thing on the right and how much work. How much is it on the left? Like, is it on the order of 10 group elements? Is
It's
it on the order
definitely logarithmic. It's definitely logarithmic. But concretely speaking, I don't know. Yeah, I have to check. I don't know. It's logarithmic. And interestingly, this problem of lane check, like proving that this lane check holds, is actually done for free in previous circuit-specific SNARKs like Groth16, Pinocchio, and all of this BCT v14. Like in all of them, these linear checks are kind of free, like baked into the algorithm. And it's kind of guaranteed by the AGM.
Okay. Actually, I know how to answer my question.
So the Groth16, it has like very it does not have a transparent setup, right? Like the CRS is very like specified. It uses those knowledge assumptions, right?
Groth16 doesn't use knowledge assumption. It uses AGM. But the previous works.
But like AGM
is knowledge assumption.
Yeah. But I'm using knowledge assumption as some overhead, like concrete overhead. You have to do this shift of exponent and prove stuff. So yeah. But essentially, everything that we can prove on knowledge assumptions, you can also prove in AGM.
Like, are you trying to do like transparent setup of the CRS?
No, the CRS is
No,
circuit
they're
specific.
also circuit specific.
Yeah.
So.
Okay.
What we're proposing is that we can somehow kind of borrow their lean checks for our PIOP checks, okay? And get the best of two worlds. Yeah. Okay, so this is the problem. So a natural question would be, okay, come up with a new lean check. So how can we do lean check without doing all those works? So we propose that we do lean checks by coefficient equality check. What does it mean? So it's a very known, it's like a known technique. It was introduced in GGPR 13. It says that, okay, when you want to prove that a known matrix times Z is equal to ZA, like you're arguing that you know a vector Z such that if I multiply A to Z, you get a vector ZA. That's the argument you want to make. So on the right-hand side, you can see this algebraically. Okay, what you can do here is that you can express this link check in the language of polynomials, because we love polynomials. So what we can do is that what was proposed in GGPR 13 was that, hey, we can interpolate the columns of matrix A, and we get n polynomials. The interpolation is happening on some arbitrary domain. We will discuss that later. And we can also interpolate this ZA on an interpolation domain. So we can get n polynomials over there and one polynomial here. And we can argue that the linear combination of the columns of A with the coefficients appearing in this vector Z is equal to this final vector Z hat A. These two checks, these two are completely equivalent. Okay? We're kind of expressing that into polynomial languages. If you think about it, it's kind of appears to be trivial. Okay, and similarly, we can do that for ZB and ZC. So we kind of transform this lin check to coefficient equality check. Okay, and the statement of the prover knows a vector Z such that ZA equals to AZ and these two statements is completely equivalent to the statement of prover knows a vector Z such that you can express Z hat A, Z hat B, Z hat C with the respective column interpolations with the same vector Zi. So if you look at this, all three of these polynomials, Z hat A, Z hat B, and Z hat C, all of them are described with the same basis under the interpolations of the columns. Okay, so we call that the coefficient equality property. We will talk about that later. Okay, the same coefficients. So let's replace this linear check that we were talking about with a lin check with a coefficient equality check. So the question is how to enforce this coefficient equality check, and that's where equifficient polynomial schemes come. It's a kind of a formalization of how can we perform this lin check in the polynomial commitment scheme level. Any questions so far?
Maybe a very stupid question. Does what kind of knowledge does the verifier have to know in the lin check?
Basically, he has to know the matrices A, B, C, right?
And
So,
then what else?
yeah, that's it. You send this Z hat ZA, ZB, and ZC, and the verifier has access to A, B, and C somehow. We don't say right now what is this access. And at the end, we need to prove that there exists some Z, and we know that Z such that these three equations hold. Okay.
Do you have to send ZA or is it like?
Yes, we have to send ZA, ZB, ZC. We have to somehow send it.
Can you go back to the previous slide for a second?
Yeah.
This one? Yeah. So actually, I think it was the next slide because you might have went back a slide.
This one?
Yeah. So if you need to do this, don't you just take the polynomial Z and you sort of just like, I mean, all sum check sort of things, you can take this polynomial Z and then multiply it by this polynomial A.
What is polynomial Z?
Oh, it's you make Z also. Okay, never
Yeah,
mind.
you can interpolate.
Yeah, you interpolate Z also as a polynomial,
Okay.
and then if you like, you need your polynomial scheme to be like kind of homomorphic. You maybe take. Okay, never mind. I have some. Never mind. You can keep going.
We can talk after that.
Yeah.
When you say you send ZA, it's sending commitments to that. Right?
Yes, we somehow commit to the ZA, ZB, ZC, and ABC are kind of committed from before. It's like a holographic setting. Okay.
Like, yeah, so you would evaluate Z at a random. Okay, never mind. Never mind. Keep going. Sorry.
Okay. So we will plug in this equifficient polynomial scheme. So let's formalize the equifficient polynomial scheme, or for short EPC scheme. So first of all, let's define what a coefficient equality constraint is. So we say that we defined a coefficient equality constraint via three basis sets. So A, B, and C, each of them are basis sets, which have n polynomials inside them. Okay. A is a basis set, B is a basis set, and C is a basis set. they're all coming from the interpolations of the matrices. Okay. We define equifficient constraints such that we say z hat A, z hat B, z hat C, they are all equifficient corresponding to these three basis sets, such that we can express these three polynomials with the same coefficients under their corresponding basis sets. Okay, so these z hat A, z hat B, z hat C, all of them have the same coefficients under their corresponding basis sets. So we can say that z hat A, z hat B, z hat C satisfy E. Okay, this is the definition. Okay, and we define EPC schemes, coefficient PC schemes, which still has this setup just like a PC scheme, but here we additionally have this specialize, which says that, okay, given the public parameters that are outputted by the setup and the equifficient constraints, this is some equifficient constraints, we don't care where it comes from, but at the end we will see that in order to construct the SNARKs, this equifficient constraints is ABC coming from the matrices ABC. And it outputs committer key, verification key, and the opening key. Okay, say opening key is inside the committer key, you can just assume that. It's not an important thing. So this is this additional algorithm that comes between setup and the interaction. And the sender now starts committing. Now we want to commit to T different polynomials. So the sender wants to commit to T polynomials, it will output a commitment to the receiver, and the receiver wants to evaluate all of these polynomials on a random point Z. And the sender does this evaluation and sends and computes the opening proof and sends the opening proof with the evaluation to the receiver, and at the end the receiver accepts or rejects. So if you think about it, this is almost the same as the PC interface with this additional specialized algorithm in the middle. Any question? So kind of specialize this PC scheme for certain equifficient constraints. Unfortunately, this specialized algorithm samples private randomness. So like the way that we know up until now how to do these EPC schemes by sampling private randomness here. But if we solve this, we get universal or maybe transparent stars. But right now, the only way we can do this is by sampling private randomness here, which unfortunately puts us in circuit-specific stars.
The way they private randomness, does it mean like I have a trusted party that sample the randomness and then throw them out?
Yeah. And we will see how that happens. And these keys are specialized for that equifficient constraints. Right? It only works for that equifficient constraints. Okay, this is just the interface. And I will go to the properties of an EPC. It will get more clear at how it works. So we have this completeness notion in PCs. We still have this completeness, which means that if these evaluations are correct, the verification has to accept. Okay, we have this additional condition here, which says that if the evaluations are correct and the polynomials that are being committed are equifficient, then the receiver accepts. So we have this additional statement here. Okay, and the same happens for extractability. So with the extractability of a normal PC, we had that if the verification accepts, the prover must know a polynomial such that these evaluations are correct on that polynomial. Okay, but here we have this additional constraint, meaning that if the receiver accepts, we can extract polynomials from the prover such that these evaluations hold. And also those extracted polynomials are equifficient. They have the same coefficients with respect to these basis sets encoded here.
Could you explain what you're trying to do? Commit with PC in lin check.
In lin check, so generally an EPC allows us to commit to several polynomials, like to n polynomials. And we can argue that the evaluations are correct on these polynomials. And also we can argue that these polynomials have the same coefficients under some basis sets. This is the second guarantee that comes with EPC. This is the only difference between a PC and an EPC. Okay? So we're kind of moving this linearity check from the information theoretic part to cryptographic of the program. Okay, so just two conditions were added to the completeness and extractability of our PC schemes. So what is our SNARK constructions? Again, we use this template, but now we have a more complicated PC and less complicated PIOP. Okay, we kind of shifted the responsibility to the down. Our PIOP only checks the nonlinear checks or row checks, and our EPC does the linearity checks, and of course is responsible for opening and committing to the program. So that's our compiler. So the way we do it is exactly like before. In the setup, we call the EPC setup, but here we also call this EPC specialized. So the basis sets that the public parameters of this EPC are specialized for are coming from the R1CS instance. Okay, that's the crucial part. So our EPC is a specialized for this ABC basis sets coming from the R1CS instance. All right, and we'll output commitment key and verification key, and the overall SNARK key are just the commitment key and the verification key coming from the EPC, and the prover and the verifier will again interact as before. They just commit to several polynomials. Never mind. I mean, don't mind those polynomials. I mean, they're just arbitrary polynomials. You just commit to several polynomials, send the commitment, and get back the challenges. And then at the end, you will open those polynomials and do the decision and the EPC check. This is the exact template that we use for PC plus PIOP. No difference. The only difference is this EPC specialized here. Okay, any question? And we can carefully transform this with fiat chemi to get non-interactivity. Why do I say carefully? Because we know that if we compile a PIOP with a PC, we get the state restoration soundness. But we don't know that if we compile it with EPC, we still get the state restoration soundness. We will prove in the paper that we still get. Okay, so what are properties of our construction? It is complete. That is a trivial property to check. And the proof of knowledge says that, okay, when the proof of knowledge works like this. So right now, we don't rely on knowledge soundness of the PIOP. The PIOP just checks a simple nonlinear check, so it only needs to be sound. In contrast with the previous PIOP-based SNARKs, that the PIOP had to be knowledge sound. That's the difference. So our extractor just invokes the EPC extractor and extracts the polynomials from the EPC. And using the soundness of the PIOP, we just checks that the nonlinear checks hold on. Okay. And additionally, we show that all of our PIOPs are round by round sound. And if we compile those with EPC, we get state restoration knowledge soundness. And the efficiencies are exactly like previous PIOP-based SNARKs. Our proof size is just the size of commitments plus the evaluations plus the proofs for that evaluations. And the prover time is just time for the PIOP prover, time to commit to those PIOP polynomials, and time to open those PIOP polynomials. And verification time is the PIOP verifier and time to check the query evaluations on those polynomials. Okay. And note that currently our construction is not zero knowledge, and it is not trivial to make it zero knowledge, surprisingly. For the old PIOP plus PC schemes, just to make them zero knowledge, is to add random multiple of vanishing polynomials to the polynomials that are going to commit, and you're done. It will be zero knowledge. But here that doesn't happen. For now, we're working on it. We have a solution right now. But the problem was that if you add some vanishing polynomials to your committing polynomials, you're kind of messing up with the basis sets. So you can't have this Equifficient property anymore. Okay. So yeah, that was a challenge, but yeah, we're adding this to the paper. Okay. So now let's instantiate this template in two regimes. If we instantiate it in univariate regime, meaning that we design a univariate PIOP for the nonlinear checks, and we design a univariate EPC, we get Pari. And if we instantiate in a multivariate setting, we design a multivariate Groth16 PIOP, and we design a multivariate EPC, we get Garuda. Okay.
Could you comment on why using the EPC scheme will lead to like better efficiency compared to like just PC scheme? Is it going to be like a batching thing or something like that?
Efficiency in what? Like,
So why is it faster? Because like right now you present a definition and like. what's
so
the
in terms of prover
institution-
time,
Yeah, so basically if we express like the EPC in like a naive PC way, we can probably do it, I guess.
yeah, so in terms of prover time, the thing is that, okay, we're replacing that linear check parts. Linear check means more commitments, more evaluations. More evaluations and more commitments means more cryptographic operations, okay? But we're saying that delete that part, just keep this linear part, the nonlinear check part. And in order to commit these polynomials, just use our new commitment scheme, which we call EPC scheme. And it has a very low overhead. So what it means is that you're getting rid of all these operations here. You're just keeping this operation with a bit of overhead on all of these commitments and openings. That's it. That's the efficiency comes from. And in order to reduce the proof size, we will see that we use another techniques that we will go through now.
Yeah, just a question from Kwang. So is it the case that expressing circuits in square R1CS is generally twice as expensive as plain R1CS?
Very good question. I will get to that. Yeah, like the worst case is like at most you have to pay twice the number of constraints. It's a constant factor here. But in Pari, we only focus on the proof size and we don't care about prover time.
Okay. What is your prover time in general?
We didn't implement Pari because we were just going for the proof size, and proof size can be just computed by hand.
Okay.
But yeah, I just for a rough.
But your asymptotic prover time?
The asymptotic is quasi-linear.
Some quasi-linear.
Yeah, some quasi-linear. You can just assume that it's okay. It's 2 log 2 worse than Groth16 at most.
Okay.
Because it's quasi-linear and the number of constraints are at most twice. So you have to pay 2 log 2. Okay. At most. Okay.
Got a side question.
Yeah,
So
sure.
why did you name them this?
Yeah.
That was the one.
That was a compromise between me and Pratyush. So Pari I'm from Iran, and it's a Persian word meaning fairy. It's a little angel. So because of the succinctness, like it's the smallest SNARK. So and Garuda is a mythical figure in the Indian mythology. I guess it's supposed to be fast. I'm not sure. Yeah. And Pari is also an Indian mythology figure, so I lost in this compromise.
Yeah.
Thanks.
Okay, so both of them require circuit-specific trusted setup, but it's a good research direction to see how we can make them universal. Okay, let's talk about Pari very quickly. So we have to first design a univariate EPC and univariate PIOP for the R1CS row check and compile the PIOP. And then at the end, we will see that we don't get 2 field elements to group elements, so we have to do some optimizations, and we'll see that how we can do it. Okay, let's say design a univariate EPC. So we will use the KZG template to construct an EPC, meaning that we want to construct a PC that also proves something else about the polynomials, which means that they're equifficients. So the simple technique that we use, suppose that we want to, first of all, let's go through KZG commitment for a refresh of mind. So let's say we want to prove in KZG that for 2 polynomials P1 and P2, we want to use KZG. First, we sample powers of tau in the setup, and in order to commit that, we compute those polynomials on the exponent on the random evaluation point tau. Let's let's act like we don't know about batching. Okay, it's just it's a canonical way to commit to those polynomials. And for openings, we compute two witness polynomials and we commit to those witness polynomials. And for checking these evaluations, we do several pairings and verification
So why are you
process.
committing to two polynomials, not one? Why P1 and P2?
Oh, this is an example.
Oh,
Yeah, I'm talking
why are
about,
you giving the example of them two polynomials? Are you going to use that later?
yes, I'm gonna use it. So I'm just, we're just gonna see that, okay, how committing to two polynomials happen in KZG world, and how can we use this template to build EPC such that we commit to these two polynomials and we also prove something more, that they are equivalent. Okay, this is a template for KZG without batching. So what is our KZG based EPC? So our EPC, the setup is exactly like KZG. You just output powers of tau. Okay, the specialize, what happens is a specialize is that having the basis set E, like two basis sets A and B, you want to specialize the public parameters to get CK and VK, specialize for these two basis sets. And later on, we wanna argue that P1 and P2 are equivalent. So what we will do is that the commitment key carries these powers of tau. We had that. The diff between KZG and EPC is written here with green. Okay, you can see that we add this to the commitment key. What is that? That is another basis evaluated on point tau and exponentiated, just like this basis set. So powers of tau is a basis set, exponentiated with this group element, and just monomials computed on a random point tau. This is also another basis set, but the way we construct these basis sets is via two trapdoors, alpha and beta. So we kind of randomly combine the two basis sets given to us to be a specialized algorithm. And we create a random basis set by them by using these two random trapdoors. And we also add these two group 2 elements to the verification key. So that's the specialized algorithm. Okay, and now we will see how we use them in commitment. So in commitment, we again commit to C1 and C2, just like before. But here, we also add a third group element to our commitment, which is consistency commitment. So consistency commitment, meaning that we want to commit to these two polynomials under that second basis set that we added to the CRS. Okay. So this consistency commitment says that you commit to polynomial P1 under this basis set. But it happens to be because P1 and P2 are equivalent, they have the same coefficients. These two evaluations are the same. So it doesn't matter whether we commit to P1 via this random basis set, or we commit to P2 with this random basis set. They both are the same. Okay, so we add this consistency commitment to the KZG, and the opening is exactly like KZG. And in order to verify, we have those two pairings. And at the end, we have an additional pairing check that wants to check that this consistency commitment is actually consistent to those separate commitments C1 and C2 with this random linear multiplication. This is the overall idea, and this is the whole interface of our EPC. Okay, any questions so far? Cool. So right now we have 3 group elements for commitments and 2 group elements for opening. So we are far from having 2 group elements and 2 field elements for pairing. So we have to somehow optimize this. The first, okay, let's talk about optimization at step 4. Let's first design a univariate PIOP for R1CS row check. This is actually kind of old technique. So this is pretty easy actually. So we want to design a PIOP, univariate PIOP, to argue that this Hadamard product holds. So Z hat A, Z hat B, Z hat C. we're gonna argue that on each row, on each of these points in this domain, this multiplication holds. So the way we do that is that we define a vanishing polynomial T of X that vanishes over this domain. And to argue that that multiplication holds is equivalent to argue that this vanishing polynomial divides this, and it is equivalent to arguing that we know a quotient polynomial such that this equation holds. So this is a known technique. I won't go into that. So the PIP prover just sends z hat A, z hat B, z hat C, and this quotient polynomial. And the verifier just randomly queries these four polynomials and checks this equation and will be convinced by Schwarzschild. Okay. This is a simple PIP for row check. As I promised, row check is pretty easy. You just send constant number of oracles and constant number of queries. In practice, we will replace it 1 through m with a FFT-friendly multiplicative subgroup. Okay, let's compile these two guys. If we compile these two ingredients, we get 5 group elements for committing. So note that we're committing to z hat A, z hat B, z hat C, and Q. And 1 consistency commitment. So we have 5 group elements there. And we're opening these polynomials. So we have 4 group elements here. And we will have to send the evaluation for these guys. So 4 field elements here. So nowhere near 2 field elements and 2 group elements. How we can optimize that is the question. So first of all, the trivial first step to optimize the proof size, which we will see that we don't use that in proving time optimization. We don't do batching there. Is that you can batch your commitments and you can batch the openings. So we can bring down those 5 group elements and 4 group elements for opening to just 2 group elements. Okay, so we went down from 9 group elements to 2 group. And the second step of optimization is that we just note that here we only focus on the proof size. So we do whatever we want to do just to optimize the proof size. So instead of using R1CS, we use a square R1CS. Now we can talk about that point that Kwan mentioned. A square R1CS at most has a constant factor blow up in the number of constraints, at most 2 times. So just, yeah, you have to keep that in mind. So how does this optimize the proof size? Instead of sending evaluation for VA, VB, and VC, we just send evaluation for VA and VB. VC is gone. We don't have any VC. Right? So this is the second step of optimization. We're still so I promise you 2 group elements and 2 field elements. Right now we have 3 field elements and 2 group elements. We have to delete one of these field elements. So which one is gonna be? Okay, the trick that we use here is that, okay, if the prover is honest and this equation actually holds, this VQ is equal to VA squared minus VB over VT, and because the verifier actually knows this VT, we can just not send this VQ, okay? Because VQ can be derived on the verification side, okay? So the only thing that we send is just VA and VB, that's it. Because this VT can be evaluated by the verifier. And at the end, we get 2 group elements and 2 field elements. So that's the optimization we do for Pari. Okay.
Groth16 is how many again?
Groth16 is 3 group elements, like 2 G1 and 1 G2.
Is that, so that's like a little bit more.
That's 192 bytes. We are 160 bytes.
Okay. So quick question about this then. So a typical application is like landing things on blockchains, right?
Yeah.
And then you want small proof size and you want a lot, you want very little gas spent to the verification. So what you've done is you've made the proof size smaller but now you've kind of encoded VQ in these other values implicitly. Does that increase the verifier time in practical situations?
Very good question. So in our evaluations, it was not so like, okay, as I mentioned, the evaluations for Pari is not done. We haven't posted them on the paper. But what you're saying is that we have to also implement that in Solidity. Like we cannot just say that on like evaluations on Rust. So I cannot promise you that. The only thing that I can say right now is that I cannot promise it. I have to check that. But yeah, there's need for implementing this Pari in Solidity and see what the gas cost is.
It's very cool either way. Getting this, breaking
Yeah.
the bounds or getting by the natural intuitive bounds is fantastic. So I'm not.
Yeah, sure. So even if we don't get good verification time, we can still use it in compositions, like the second part of the compositions.
So another question is that, so it seems like one of the optimization was to consider square R1CS.
Yeah.
What happens if you consider like square R1CS for like Groth16 or something? Does the proof size also shrink in a similar way?
Well,
Because maybe
it's
you
not
don't have to
trivial.
use-
Like Groth16,
Cause you don't have to send the C component anymore. I mean, I don't exactly know the details of what the proof like is.
yeah.
But I feel like if you were to say you are more succinct than Groth16, then you'd have to consider how Groth16 performs over square R1CS.
What I can say is that we actually have that construction, I suppose. Yeah, there's again this paper by Groth and Muller, I guess, that they used the square R model. Actually, Groth himself introduced SR1CS.
Right.
So I'm sure that he tested this idea. So yeah, I'm not sure exactly, but I'm sure that there's a paper using the exact technique for SR1CS and didn't manage to bring down the proof over. Okay. So very quickly, or Garuda, I know that I'm over time. So what is the diff between Garuda and Pari? Garuda uses generalized R1CS. It allows us to use arbitrary custom gates. It uses multivariate EPC, which allows us to use free addition gates. It is also the case for univariate EPC. I'm just saying that the EPC itself uses free addition gates. And we use multivariate row check PIP, which gives us a linear time prover because we use multivariate sum checks. Okay, what is generalized R1CS? It's not a novel contribution, actually. It's equivalent to CCS, customized constraint system, if you've seen the paper. We just used this because we found it easier to work with on the programming side, on the user experience. So what is R1CS? It's a predicate of the form AZBZ equals CZ. What is SR1CS? It's a predicate of the form AZ squares equals CZ. So what if we extend these predicates to an arbitrary form? Say AZBZ CZ to power 4 minus BZ power 3, blah, blah. And also this predicate can be of the form of a lookup table. And say tau of AZ of something. Tau means that if this element exists in the table or not. So this predicate can be arbitrary, any function, okay? So generalized R1CS says that, okay, you can just define your predicate, L, and you can define an array T, and you can get T matrix vector products as an argument, and you can decide whether it accepts or rejects. Okay, so a GR1CS instance allows us to define many predicates. You can have lookup tables, you can have high degree gate, you can have R1CS, SR1CS, all of them in the same circuit. So this is the notion of GR1CS. You have LIs, different predicates. Okay, that's just GR1CS. So we also have the programming interface to program GR1CS. It is not public yet. It will be public in a couple of days in ArcWorks. So you can use ArcWorks to program your different arbitrary predicates and synthesize it into a circuit. Hopefully soon. Okay, so how do we use Garuda? How do we build Garuda? So in GR1CS, we have C different predicates. Like say you have L1 through LC, each of them have their own matrix sets. Like L1 has its own matrices, LC has its own matrices. The way we design Garuda is that we first stack these matrices on top of each other. And instead of having many predicates, we get one predicate, one big predicate, okay? And this is the exact definition of CCS. As I mentioned, it's not a novel thing, but yeah, stacking is a new technique that we're using, but after stacking, you get something very similar to CCS. Okay, so you get T big matrices and one mega predicate. And what we'll do, we just prove the satisfaction of this big predicate. And the way we do it is that we use selector polynomials. So each of these selectors, S1 through SC, kind of turns on and off each of these predicates at certain locations of the domain. So we have a big domain, and we kind of specify each portions of this domain for different predicates. And at the end, so yeah, these are the selectors, and at the end, we do a zero check on this big polynomials. So we kind of prove that this huge polynomials is equal to 0. That's exactly the same approach that, if you think about it, Plonk does. Selectors times predicates. Yeah, so there's this grand zero check, and we compile that with the multivariate EPC, and we get Garuda. Okay, so there are a bunch of open questions at the end. Unfortunately, our EPC constructions use private randomness. They're still updatable, by the way. We can update that SRS. We cannot update tau, but we can update those alpha and beta. Whatever. So unfortunately, this circuit is specific. The question is, how can we make it universal? Like the only thing that I mentioned here, like the takeaway from this talk is that we don't need to do everything on the PIOV side. We can do some of the checks on the PC schemes. And right now, like yeah, Matan and I were talking about like how can we extend these linear checks on the code-based PCs? Like how can we do that natively on the leveraging code structures? So yeah, so if we have an EPC that is good, we have a SNARK that is good. That's a takeaway. And the other open ideas are like what are other applications of EPC? Where else can we use them? How can we accumulate them, for example, in recursive SNARKs? And this is actually outdated. We now know how to make it Z cases. Yeah, don't pay attention. Yeah, cool. That's it. Thank you.
Thank you, Ali.
10 minutes over time, sorry.
That's okay. We also started a little bit late, so
Okay.
maybe only 5 minutes. Yeah. Any questions for